are you doing course notes or I see that Criver did this PDF here about the chapter 2.
You can think of this as a summary, this chapter 2 PDF.
Yeah, but are we doing course notes like we in general? Because I can
If you
help
want
if
to, so
needed.
no. So there's nothing mandatory. Uh, Basically, if you want to review something, you can write yourself a summary too, just to make sure, okay, you understand things, etc. And if you want to, I can look through that PDF, the one you write, or text, or whatever, even photos of notes taken. But otherwise, there's nothing mandatory. So there's no coercion for you to read the book or anything.
No, it's okay. I was just like offering some help because I can do some chapters and just
Are
that
doing
so
course.
you don't get overloaded with work.
Yeah, thanks for the suggestion. If I don't really have time, because yeah, I'll have paper submission January and February. So yeah, we'll see.
Okay, thanks.
Yeah, thank you. So Cyrax,
Yeah,
are you recording?
yeah, I am.
Okay, thanks. Okay, then we'll continue with this PDF. So uh, the main thing that's introduced first are the radiometric quantities, and what's not made clear in the book is that this Q, so your measure of energy, it's over some different sets. So your detector can have an area, which in my PDF is this D, a set of points. Just imagine like a flat disk or something where you just detect the amount of photons that fall. And you obviously can detect that over some period of time t. That's the first argument of the function. Then you also may be able to just detect photons coming from specific angles. So that's the omega set of directions that you detect photons from at each point of your detector. And finally, you may detect photons only within some wavelength range. So that's the lambda. And then you see then Q is of the form T, D, omega, lambda. So it's a function of 4 sets. And that function takes values from 0 to infinity because it's energy. You cannot have a negative energy here. Is that clear? Any questions on that?
Yeah, I'm just wondering if it would be easier if you would share your screen and then you would show where
Okay,
exactly you're in the PDF.
let me
Yeah,
try
that's
to
right.
do that. Okay.
I can't.
You can't?
Oh wait. Oh yeah, actually I can see it. I can see.
Yep.
Yeah, looks good.
Okay, so in the second chapter, you have, let me just pull out the second chapter. Yeah. Let's see. Okay, the second chapter starts with a definition of flux, but even before that, so before you define flux, you can define the energy in your scene. So just imagine a detector that detects the photons falling on it. And that detector has some area, surface area, so the set of surface points would be M here, and you can pick a subset where you want to measure, so D. You have some interval of time in which you can measure, so that would be t, the set t. You have some set of directions that you want to consider. Usually that will be the whole sphere, but you can obviously measure photons coming only from specific directions. And finally, you have some an interval of wavelengths that you want to consider, so that would be lambda. And you get a function that measures your energy in the scene, that would be your detector, which takes values from 0 to infinity. Energy cannot be negative. Any questions on this specific thing? Is the analogy clear?
It's okay. I just want to know if the subset of directions is the upper hemisphere over the differential, or
Huh?
is it not?
No, these
Yeah.
are sets. These are currently sets, just sets of points, and these would be sets of points on the unit sphere, or a subset of those. So omega is a subset of points on the unit sphere. This S squared is the unit sphere.
Okay. Okay.
So is the analogy clear? Not? Yes?
I'd say
Yeah,
Specific
it's
so.
pretty
question
much okay.
made?
Yeah,
Yeah,
I'd
it's
say so.
clear.
Yeah, it's clear.
Yep.
Okay. Then in the book, what they fail to mention obviously is that these E, these M, B, L, these are functions of sets or also functions of points. So how do we get from a function of sets, this Q here, to a function of points? Well, you take the derivative. This is a Radon-Nikodym derivative, so I won't go into the details of that. You can find some details in Vich's thesis and also in the math preliminary that I shared in the chat a few days ago. So how do you define the flux? Well, it's simply the derivative of the energy with respect to time. So you can imagine making this t, this set t, smaller and smaller, and dividing by the size of the set, so the length of the set. Maybe I should pull out the math preliminary to just a second. I'll share that for you too. Still not fully unfinished, but this is called, yeah. See. Okay, I shared that too. Did you see it?
Yep.
Let me just share the correct. Okay, so if you go to the very bottom, right here, you have radiometry in more details. Can you see my screen? I assume you can.
Yep.
So
Yeah.
Yeah, perfect.
if you go here, you can see, okay, let's just take some small subinterval starting from t prime to t prime plus delta t divided by delta t. So that would generally, intuitively give you the average energy per unit time. Now, if you make this delta t infinitely small, well, you get the derivative. And now you care only about the point. So that's the flux when you make this delta t infinitely small. Any questions on this specific thing? Like, is it clear what the interpretation is, what the intuition is of making this interval very, very small? Basically, you're measuring the energy in a smaller and smaller interval, but also by dividing this energy by the time that has of this interval, so the duration. So you get something like an average. And at the limit, it's a single point, it's the t prime. I assume that's clear? Or did I
For
lost
me, it's okay
everybody?
at
Yeah.
least.
Yeah.
It's clear.
Okay, so in a similar fashion, you can define irradiance and radiosity. Now, just by taking, so for irradiance and radiosity, you take the derivative with respect to area. So once again, let's say you take some neighborhood of points, ux, around the point x, and you divide by this area. So let's go back to the initial. So you have this set D here. So that would be ux in this example. And you can obviously make this set smaller and smaller. So we imagine just a disk around the point X on your detector, and you make that disk smaller and smaller. and obviously the area becomes smallest. So once again, this is just an average of the flux this time over the area. Questions? Oh, okay, Legend has some connection issues. So I assume that's also clear. If you make this area infinitely small, well, you get the derivative with respect to the area, and you get irradiance, the definition of irradiance. So as you can see, flux is defined with respect to a set when it comes to surface, and now the irradiance is defined with respect to a point. So every time we take such a derivative, so a measured derivative, you reduce a whole set to a single point. So in a similar fashion as you had a set of time points, we turned it into a single time point. Then you had a set of surface points, we turn it into a single point to get the irradiance. And the irradiance is really, you can think of it as how much light arrives at a single point, so incident light, while radiosity is the opposite. It's how much light leaves a certain point. So let's say some light arrived and then it got scattered, or you also have emission, etc. Is that clear?
Just one thing in general that seems a little confusing to me is that like we have this this surface area, this disk, but
Yes.
then we also consider the entire sphere of incoming light rather than the hemisphere. And in that case, is the area just, what meaning does the area have? Is it like the projected area?
Okay, you can assume that your detector, so it has a surface area, right? You can assume that, you just imagine a very large disk, and you can assume that it's two-sided. So you have the upper side and then you have the bottom side, right, of the disk. And if you consider all directions around a point, they form a sphere, right?
Yeah, so it's just like the direction of the surface area doesn't play a role here at this point, or?
Yeah, currently for at least for irradiance as a derivative of the flux, no, it doesn't matter at all, like how the area is oriented or whatever, because you're decreasing this to a very, very small neighborhood. And again, you should know that omega here, it is a subset of the sphere. So you can pick anything. You can choose to measure light incoming only from some direction. Obviously, you can choose the whole sphere, or like in the book, you can choose only the upper hemisphere or some subset of it.
I see. Okay.
So it should be noted that, okay, this E, it is a function of a point, a time point, a surface point, but the other two are sets. So omega here is a set, which is a subset of the unit sphere, and lambda here is some subset of the numbers from 0 to infinity, so some subsets of wavelength. So that's regarding irradiance and radiosity. Now you can define another quantity, which is intensity. It's not in the book, I think. This should read I. Here it reads I, okay. So this is the derivative with respect to solid angle. So you consider only some subset of directions, omega prime, around a direction omega. And if you make that cone of direction smaller and smaller until it becomes infinitely small, well, you get the derivative with respect to the solid angle. So that's intensity. So once again, this is defined over a whole set of surface points, but only with respect to one direction, while the irradiance was only with respect to one point, but over a whole set of directions. Is this clear? About what intensity is, how you get it, and generally this omega prime and this omega, it would be in the coordinate system of the point x. So if you just assume a flat disk, then everything's fine. But if you have something curved, well, this omega may need to be transformed in the local coordinate system. It depends what directions you want to measure. So that's the definition of intensity. And now if you combine the two, so the derivative with respect to area and the derivative with respect to solid angle, well, you get radiance. In some sense, the basic quantity that we will work with. So it's a derivative with respect to area, a derivative with respect to solid angle, and you have also a cosine. Either you can think of this as coming from Lambert's law, or there are some. You can also derive it purely mathematically from two forms, etc. But that's differential geometry, so I'll try to stay away from that. If somebody wants, I can link the reference for that at the end. And again, you can see that your radiance is a function of a point in time, a point in space, a direction, and also some range of wavelengths. Now, if you want to also get, let's say, a spectral renderer, well, you need the spectral radiance, which also takes a derivative with respect to the wavelength. Not much different than taking the derivative with respect to time, so it's a 1D quantity, and you get exactly what you want. So yeah, how do you compute this cosine here? Well, it's simply the direction that you consider for the radiance dot product with the normal at x at this point that you consider. Is this clear? Any questions? Because this pretty much covers the what you have in the book for the first few pages.
So yeah, I find that the definition of intensity is pretty similar to the definition of radiance. The difference, I think, is that the definition of intensity, you consider the whole set of points, and you just consider one
Yes.
point at the definition. Is that correct?
Yeah, that's correct. So you can think of it, it's basically irradiance. You have, okay, a derivative of the flux with respect to area. And intensity, on the other hand, you have a derivative with respect to the solid angle of the flux. And now for the radiance, you have two derivatives. So once with respect to area and once with respect to solid angle. So you combine, you technically combine both irradiance and intensity, and you get something like something more fundamental, let's say. But you also have this cosine here, so don't forget that part. That's important.
I also see in your definition of radiance you have an absolute value on the cosine.
Yes,
Well,
because I'm considering the whole set of directions on the unit sphere. So
okay, I see.
if in mathematics you may have surfaces that have, let's say, that are oriented, so they have a normal that points only in one direction. But you want the correctly facing normal, so you would take the normal that gives you a positive value. That's what the absolute value here is for. So it's technically, this is, if you work with refraction, transmission, etc., you need this absolute value. If you just work with reflection and scattering in the upper hemisphere, so just working with BRDFs and not BSDFs, then you don't need the absolute value.
Okay, yeah.
Other questions? No? Okay, then I'll continue on to radiance. So we have the definition here of radiance, which is, okay, some kind of derivative of a flux. And in the book, they don't make it very explicit, but they have two definitions of radiance. And one is excitant radiance, the other is incident. So for incident, we would use, so it's two different functions. We would use Li or L left arrow, or like this, like in the book. And for excitant, we would use L without anything, or LO, which is outgoing. I here is for incident or incoming light, or right arrow, or similarly like that. Also, what they use in the book for directions is usually for the excitant direction is theta, and the incident direction is psi. In other resources, you can find excitant as omega O, so outgoing, and omega I for incident direction. So what are directions? You can think of them either as unit vectors, so something on the unit sphere, or you can parameterize them in spherical coordinates too. It's fine. So it's a two-dimensional quantity because the length is always kept at 1. Questions on that? Is it clear what it means for light to be incident at a point from direction omega, or to be exitant from a point x in direction omega?
Yeah, this is clear.
Yeah, it's okay.
So something which may not be made clear in the book is that the directions, you should always think of them as having, so think of a direction vector as always having the tail of that vector on x. So even if the light is incident, this omega or theta or psi would point away from x. That's just the convention they use, and they use it because it makes some mathematical properties nicer for making some operator symmetric. But just remember that these directions do not necessarily match the flow of light. They just always point outwards from the point, so never towards it. And that also helps with having the correct dot product here. So you do not have to flip omega even if you assume that the light is incident. Okay. Next, we will define the ray tracing function, which is simply you give it a point on a surface and you give it a direction, and it finds along that ray the first intersection. So this Rx omega would give you some point y if it intersects anything in the scene. And then you can also rewrite these functions that were in terms of a point, a position in space or on a surface, and a direction in as a function of 2 points. So from x to the point that you intersected. Questions on that? I'm assuming most people have written or ray tracer here, so they should know how ray tracing function works. Okay, energy conservation along a ray. So in the book you have a statement that energy is conserved along a ray if you assume vacuum. So if you have a point x on a surface and you shoot a ray in direction omega, then the radiance leaving, the radiance leaving from x in direction omega, it's the same as the radiance arriving at whatever you intersected at the other side, some point I from direction x. So the energy leaving x in direction y is the energy that arrives at y from direction x. Is that, I think this is pretty self-evident, but it's stated just so it's clear. You should not make the mistake that so you have this equality and not this equality here, which would mean that the light leaving x in direction omega is equal to the light arriving at x from direction omega, which is not true. So the light leaving x in some direction doesn't have to be equal to the light arriving at x from the same direction. Is that clear? Just never confuse the two statements, this one and this one. So this is not true. These are generally not equal. These are equal.
This is okay, but I have a question about is light? Are we assuming that light is not attenuated with distance?
Yes. So if you assume that there is no participating media, so you assume that your scene, you assume that you only model the boundaries of your object, so only surfaces. And between surfaces, you assume that there's only vacuum. So the light that starts from a surface point leaves it in some direction, it arrives at the intersection of this ray with some other surface point, the very same light. So it's not attenuated with distance. Okay. So I think I understood what you mean. So you mean light and not, so radiance is not attenuated. Irradiance, on the other hand, like this thing here, it does follow the in inverse square law. So you would have a fall off. So if you imagine a point emanating light in every direction, so a sphere that grows, then as that sphere grows, yes, the energy on the surface of that sphere would be smaller. But this is radiance. So radiance doesn't get attenuated with distance, and you can see that. So if you look at the sun I think they had that example in the book. If you look at the sun from the Earth or from Mars, it's as bright if you ignore any atmospheric effects. It's as bright from both directions. It just looks smaller because it's further away. But the radiance, so the energy that comes along the ray, it's the same. Is that clear?
Yeah, okay. So as far as I understood, the light gets attenuated with distance, but radiance does not.
Well, light. Okay, I'll use light interchangeably with radiance. So not exactly. If you imagine, but if you imagine that you have a sphere around your, let's say you have a point light, right? And
Okay.
imagine you want to measure the energy in a sphere around that point light. The further away you go, the less energy you have per unit area. So that's true. So both are true. So radiance doesn't get attenuated with distance, and light as a particle or as a ray of light, it doesn't get attenuated. You don't have attenuation of a ray of light with distance. But if you consider not radiance, if you can consider, let's say, flux or whatever, that gets attenuated with distance because because you measure it over some surface area. So if you grow the surface area, obviously you have less light density per surface area. So if you grow a bow, imagine you have a bow, and at every point you have some allocated some energy, and that bow grows. Well, the energy, the average energy per point decreases because the area increases. Is that clear?
Oh, okay, I get it. So the flux is the one which gets attenuated with distance,
Well, stuff
and
that
energy does not, because a particle carries the same amount of energy in the vacuum,
yes,
regardless of whatever distance it runs.
yeah, you can think of it like that, I guess. So this is really about energy conservation, and it lets us basically do this in the mathematical formulation. We can flip things if we flip the direction, so that's nice. Okay, next thing
All right.
is how do you connect the solid angle? So if you have a direction to a point where you shot your ray at. So you have some point X, you have a direction omega, you shoot a ray, you intersect Y, and now the question is how can I connect the two differential quantities, the solid angle quantity as a function of omega and the differential area as a function of Y? Well, it's just the cosine at the norm of Y. I think that's, let me check I think they have a nice drawing for this thing in the book. Okay, yeah, here you have it. So let's say I shoot from X a ray in direction Y, it hits Y here, and I want to know, okay, what's the correspondence, so this thing, of the differential solid angle and what you have for area here. And it's the cosine of this angle divided by the distance between the two, multiplied by dA, obviously. Yeah, so for that, you can either take my word for it or the book's word for it, or as mentioned, I can link you a reference that's purely mathematical for this specific thing, but it does go into differential geometry.
I
So
think
that's,
it's
yeah,
yeah, I think it's explained in Appendix B, right? In
they
hemispherical
don't derive
coordinates.
it. So they never
Oh,
they never derive
mhm.
this.
No, right, right.
Like formally you can obviously make some intuitive remarks, etc., but this is never derived, And the derivation is not very easy either. So for people that are interested, I can link the relevant material, but yeah, it's not even derived in Veitch's thesis. It just postulated this. You say, okay, the relationship between solid angle and surface area, well, some cosine pops up and then you have the distance. So either just take it as it is or you look up the relevant thing. So why do we need this? Well, we will need this to connect the solid angle formulation of the rendering equation and the area formulation. But okay, 25 minutes passed, so we'll take a 5-minute break. Is that okay with everybody?
Of course.
Any objections? Okay.
It's okay.
No. Yeah, it's okay. Yeah.
Okay, see you in 5 minutes then. Of the light, you can think of radiance as a laser. And you can see, okay, the laser doesn't fall off with distance. You have a nice directed stream of light. Now, what's up with the fall off with distance? Well, it's not really that light gets attenuated. It's how you measure light. Because if you measure it further away, you're kind of considering a whole sphere, and you will know that the surface area of that sphere, it's a function, it's proportional to r squared, right? So we have like 4 pi r squared. So the further away you are, the more area you consider in some sense. So the light is still the same, it just spread over a larger area where you get this r square factor from. And you can also see that, where is that? You can also see the a squared factor in the differential area to differential solid angle formulation. So what you have here in the denominator, y minus x, the distance squared. So it's only when you consider area measures. Is that clear?
That's a nice.
Does it address the question?
Yeah.
Okay. Let's continue then with the.
I have a question actually.
Yeah.
I'm just wondering if we interpret radiance as kind of a ray, then I was just wondering how would we interpret like a differential radiance?
Differential. You shouldn't currently try to interpret this, but depends what the differential is over. So if you have like, let's go back to here, for example. If you have this, where is that? Yeah. If you have spectral radiance, where is the differential radiance over d lambda, right?
Yeah.
This is just a derivative with respect to lambda. So dl, you can think of it as a in general, when you see this d in front of something, you can think of it as a very small change of this in something, in some aspect. So here it would be in lambda, small change in lambda, and you can I can show that. Yeah, like here's the small change, but it really depends on what you have in the at the bottom. If you just have dl, then it's, let's say, it's harder to interpret. Like it has some meaning, but only in some contexts. That's the point. You cannot just write dl and say, okay, that's, unless you have the context, you cannot say what it's referring to. Is it clear?
Yeah. Okay. Yeah, it's clear.
I think you're referring to the BRDF, right? Because they have that there.
It's just sometimes you have the differential radiance on only one side, and then in those cases it's a bit harder to derive what's the parameter.
You're talking about the BRDF, right? You're talking about this.
Yeah, for example. Yeah.
Okay, yeah, we'll get to that. Okay, so let's continue with how would we compute any of these quantities? Well, we'll consider our radiance here. So think of it as a ray of photons or a stream of photons in a small cylinder between 2 points, x and y, or in a cylinder formed by a point X and a direction, okay? Omega, very small cylinder. So we have a stream of photons in there. So we always use the radiance, and we always want to compute the radiance or some form of it. And we can derive the other quantities from it. So the flux, using the, if we go back here, we can see the flux. Where is it? So we can see that radiance is some kind of derivative twice with respect to area and with respect to omega. So you can take all of these here, multiply this side by those, and then multiply on this side, and then integrate both sides, and you get, where is that? You get this thing, right? Here I've left the cosine without absolute value because we will assume, like in the book assumes that omega is always the upper hemisphere, at least in the current chapter. So you integrate both with respect to the points x on the surface D and the directions on the, here it would be the upper hemisphere, and you get your flux. You have two types of fluxes. So if you consider outgoing radiance or incident radiance, you have two types. In the book, they do not differentiate between those, and they just write phi. But from the context, it should be clear what they're talking about, whether it's excitant or whether it's incident flux. Similarly, you have radiosity, which is based on the excitant radiance, but you only integrate with respect to the directions because you want to keep only, so it's a function of position. The same thing for irradiance, but it's light incident upon the point X. And then you have the same for intensity, but I don't think they use intensity in the book, so you can even ignore this for now. And this cosine is, as already mentioned, you can compute it as the dot product between the normal at X and the direction omega that you have here. And here you have this omega, so you have it from outside, and you can compute it in the exact same way. I assume this is clear, like it should follow directly from what we saw on radiometry. Questions on that? We'll compute these integrals if need be. We'll compute them numerically, so you don't have to care about, okay, how do I deal with this analytically? Questions on that part? None? Okay. And then we get to the, yeah. Did you have a, okay. So then we get to the bidirectional reflectance distribution function. So that would consider only the upper hemisphere. That's why it's called reflectance. Now, if we have scattering, bidirectional scattering function, it may include also transmission, etc. So what you can see in which thesis, it's formally defined as some differential of radiance over a differential of E. But this here, we can write it directly from the definition that we have of radiance. So you have this. If you plug this in here, you can actually get the expression for, where is that? You can get these expressions for dE. You can express it as radiance multiplied by cosine theta. And it should also be obvious from here. If you take some kind of derivative, let's say, so you add d here, you remove the integral, where you get dE is equal L multiplied by cosine theta multiplied by some differential solid angle. So that's really what you have here. So what's really the BRDF? Well, it tells you based on some falling radiance. So we have a direction in incident light direction omega I, outgoing light direction omega O, and you care about, okay, how much of the light that falls on X from direction omega I multiplied by the cosine theta, so that's for Lambert's law, leaves in direction in the differential direction omega O, how much differential radiance you have. And it will become clear why you need this gel here from the rendering equation, but let me go to the book also, just to show where this is. Yeah, so in their case, again, they use theta for outgoing, psi for incident. It depends on what resources you're reading, whether you see omega or omega I or both of those. So what important properties does a BRDF need to have to be physically based? Well, first you would expect that the energy shouldn't become negative, so you have non-negativity. So the BRDF may be zero. If it's zero, that just means, okay, all energy coming from omega I is absorbed, so nothing leaves in direction omega O. If it's something higher than zero, then some portion gets reflected. Do not think of this as a percentage, by the way, because that can go to almost infinity or whatever and still be energy conserving. So it's not a percentage. Don't think of the BRDF as a percentage. It should also be symmetric. What does this mean? Well, it means that if I shoot my let me pull the if you have this graph here, so this figure, you have outgoing direction theta and incident direction psi. So you say, okay, if I shoot some light from direction psi, how much light would I get leaving in direction theta? Now, if you flip, if you say, okay, my light source is instead at theta and my detector is at psi, if I flip this, if I flip the direction of light, does the BRDF keep the same value? And if it does, it's symmetric, and then it is then it is also would. So that's one prerequisite for it being physically based. So flipping the direction of light shouldn't change how much it gets reflected there. And then we can write this double arrow to indicate that, okay, this is, I can flip the arguments. I can flip omega I and omega O and everything's fine. It is not a problem to have non-symmetric BRDFs. So you can have those in your rendering. And if you actually go to transmission, to refraction, then your BSDF, it doesn't even need to be symmetric to be physically based. So just from having refraction, you lose that symmetry. So this is not always true. This is true for physically based reflection distribution functions, but not even for transmission functions. So that's not always necessary. And your renderer can work just fine even if you don't have this. If you have a bidirectional render, then there are some things you may take into account if it's not bidirectional. Finally, energy concept questions.
Yeah, I'm just wondering why is symmetry kind of a constraint that we want to be physically based? What's the reasoning behind it?
Well, I guess it's physics from I think it's called Helmholtz reciprocity principle. But again, as I said, this is not generally true if we are talking about BSDFs. So if you have transmission, this is not true anymore. And it's still physical, obviously. So it's still in the real world, but it's not true for when you consider also transmission. Just consider refraction, then your energy grows or decreases by the ratio of the indices of refraction squared, depending on from which direction you're looking. So this is not generally true. This is true for BRDFs, for reflectance, when your ray doesn't go under the surface and you don't have different indices of refraction. Does that address your question, or?
Yeah.
And omega is infinitely small solid angle, right?
Here you can think of, in your implementation, omega would simply be a direction. It can either be represented as two angles, so in spherical coordinates, either as theta and phi, or you can represent it as a unit vector, so vector with length 1. So you don't have to think of it as the solid angle is right here. So this is the differential solid angle. Can you see it?
Yeah,
This sigma omega I.
yeah, I meant this.
Omega I
So,
by itself is just a direction, a unit direction. So it's a two-dimensional quantity y. Even if it's a 3D vector, if it's limited to length 1, well, you can define it by only 2 of its coordinates and then figure out the third coordinate from the restriction that you need it to be length 1. Okay?
Yeah.
So technically, let's think of the dimensionality of this function. So for example, if you say I have surfaces, well, surfaces, again, they are in 3D, but surfaces are technically 2D manifolds. So what can you say about this function? Well, x, even if it's 3D, in reality, you index some texture, right? To find out the color or whatever. So it's actually 2D. So this x is technically, it's a 3D point, but to it corresponds a 2D point in your surface. So that's 2 dimensions. Then you have 2 dimensions for the incident direction and 2 dimensions for the outgoing direction. So that makes it a 6-dimensional function. I think that's clear. So if let's say you wanted to implement a BRDF and you do not want to use any analytic function, you just want to have some hypertexture. So you would need a texture that is 6-dimensional. Does that make sense? Like it's so if you have a texture, it's usually 2D. If you have a cube map, that's 3D. Now if you go to something higher, 4D, something even higher, 5D, and then 6D. So to have the most general, let's say here, version, that would be 6D. And if you add subsurface scattering, then you have another point of exitance, etc. And so it becomes even harder. So even more data. So the final requirement for probably the most important one, except for the non-negativity for the BRDF being physically based, is that the radiosity, so think of it as all the light leaving the point X, should be smaller than all the light arriving, or equal. So you cannot have more light leave than the light that arrived at that point. Otherwise, obviously, your material is not energy conserving. Like the light increases. What's the issue in this with this in path tracers? Where it could happen that so your path tracer may still work even if your materials are not energy conserving. Especially if you limit the amount of bounces, then everything may be fine. But with every bounce, it may happen that your energy increases. So if you keep increasing your energy with every bounce, and you do infinitely many bounces, well, you end up with a scene that's just over bright and everything's infinity that you measure. And for this part, radiosity over irradiance, you have this in the book. Where is that? So we have this ugly expression. So this is really the B, where is yeah. So this is really this expressed as what we have, and what they do here to simplify it. So to get, I won't go into the details of it. Maybe after the meeting if somebody wants to. So what they do to simplify this is they say, okay, we'll consider only one possible direction for incident light. And if you do that, the integral simplifies. So this ugly expression here simplifies, and you get really what I think you're familiar with regarding BRDFs. It's basically that if for any incident direction, this here integral should never be larger than 1. So your BRDF may be infinity, but the energy conservation is not your BRDF itself being smaller or equal than 1. It's really this expression here. Questions on that? I guess not. Okay, then we'll continue to the rendering equation. So if you remember, you have this expression for the BRDF. Well, try moving this to the left-hand side. So here, then you're left with DL equals to BRDF multiplied by L incident by cosine theta I by the differential solid angle. And then if you integrate both sides, so you can remove this d by integrating, you get really the solid angle formulation of the rendering equation. Where does this LE pop from? Well, it's a indefinite integral, so you always have a constant. So this is your emission of the scene. You assume some points in your scene may emit light in specific directions. If they don't emit light, you can just use LE is equal to 0. So this is your rendering equation, which says, okay, the outgoing light from X in direction omega O is equal to the emitted light from this plus the reflected light. So you consider all possible directions, you have some light falling, then you multiply by the BRDF and you say, okay, how much light does live in this specific direction I care about? And you have the cosine, obviously, because of Lambert's law. Questions on the solid angle formulation? No? Then we can
Yes.
go to the area. Yeah. Okay.
Can you please explain once more why there's an emitted radiance? Because I don't really understand.
Why there's this here, right?
Why we make the distinction between emitted and reflected radiance?
Okay. Because so every point in your scene may emit some light, right?
Yes.
That is clear. What other light may live in a specific direction except the emitted light? Well, it's the light that gets reflected. So you have light coming from other directions. Where is that? Do they have a good graphic? No. So you have light coming from other directions. Let me just find a nice chapter that has a good figure, because I don't have a good figure of this. Okay. Yeah, okay, here you have it. So let's say that you can see the book, right?
Yes.
Okay, so except for the emitted radiance in this direction, you also have radiance falling from every direction, right? You can assume from every part of the upper hemisphere, you have some light falling on that point, right? And the BRDF tells you how much from that direction gets reflected here, how much from that direction gets reflected here, how much from that direction, and from every possible direction. And if you sum these up, that's really this, where is that? That's really this integral that you see here. So does this clarify it? Where this part comes from? Does this clarify where this part comes from?
Yes.
It's basically from all the light. You want to account for all the light that is incident upon this point. And how you do that? Well, you just sum the contributions. That's what really this integral does. It sums up these contributions, but they are infinitely many and infinitely small, so it's not a sum but an integral of a solid angle. So this omega here is the psi here. So all possible directions. This, and any other directions on the upper hemisphere. And if you have the function L, then you know that. So what you may notice now is that, okay, this here, LO, we can turn it into LE. So we can change this. We can change this function into LO simply by saying, okay, find the point Y. If we start from X, shoot a ray in direction omega I, we find a point Y, and then we can say, okay, the light coming from emitted, so the outgoing light from Y towards direction minus omega I would be LO here. So then you would get a recursive integral. So it's an integral where what you're looking for, so this function, shows up so also within the integral. We'll see how to solve this in the third chapter. And finally, so does this answer your question actually?
Yes, thank you.
It's not, is it too technical? Just tell me if it is. Don't, like if it's not clear.
At least it's intuitive.
Yeah, that's why I put up the figure, because, I mean, Otherwise, you just have to rely on the mark and yeah. So the area formulation, you have this relationship. We saw it before. We saw it here also. Let me go to the relevant part. Yeah, we saw it here. The relationship that relates differential solid angle to differential area. You can see it also here. So we use that relationship to we just take the solid angle formulation, we plug this in here, so we have this expression, we substitute it with this, and then you get this expression for the area formulation, which now integrates over areas. That shouldn't be omega x, that should be m. It's over all surfaces in the scene. Where is that? Do they not? Okay, they have it explicitly. So now the integration is over all surfaces of the scene, and this is simply, G is simply, it absorbs this factor and the cosine that you had previously, so this factor. So that's what G absorbs, and V is a visibility function which really says, okay, is there any point closer to X than Y in direction XY? Because if it is, you cannot see Y from X, so is Y occluded by something? So that's it really regarding the area formulation. Questions on the area formulation? These two integrals, so this integral is equal to this integral. If you plug in here, if you fix the mistake that this should be over areas. So this integral is the same as the solid angle integral. It's just a different parameterization. Is that clear?
I have a question on the area formulation, actually. In the geometry term, we see that you took the cosines of both normals with vectors, the directions, and the denominator is x minus y to the fourth. And in the book,
Yes, because
it's a square.
yes, because x minus y is not necessarily normalized, and we want a cosine here, right? The cosine. So if you have a dot product of two vectors, the dot product is, let me show you, just so it's clear. So if you have the dot product of two vectors u and v, you have the length of u multiplied by the length of v multiplied by the cosine, right? So that's what you get by the dot product, right?
Okay.
Now, if this is not unique length, which it will not be if you just shoot a ray and find some y, then you need to normalize it. So one of these, so that's usually in the books, this is squared, but you have to the power of 3 because you want to normalize that. And then you also want to normalize this in the cosine here. So this cosine. So now this is, so your omega I is now y minus x divided by the length of y minus x, so the normalized vector, right? So that's where the
Oh,
x
I
minus
get it.
y, yeah. And in your implementation, really, it will look like this. And in here, in your implementation, you won't have some omega. You would actually have y minus x divided by y minus x, or depends. If you're sampling a direction, then you can sample it so it's unit length. So it's really it really depends. Do you have a point y? Because if you have a point y, well, you have to normalize your vectors to get the proper cosines from the dot product. So that's regarding the area formulation. Is it clear how this would work in an implementation, the visibility function? Any ideas?
How the
Yeah,
visibility will work with the.
Yeah, how would you compute whether this is 1 or 0, the visibility between x and y? What will you do in a path tracer?
Just
Path
raycast, I guess.
traps.
yeah.
Well, not quite. There's a detail there, because ray casting just gives you the first point at that you intersect, right?
Yeah, right.
So
Yeah.
what can you do better? Well, you can consider just a line segment between x and y. And if there's nothing, so if it intersects nothing, this line segment, you're done. You don't need to continue further. And because of numerical error, you would have to offset your ray a bit higher than x and finish a little before y, because you do not want to intersect any, the surfaces. Is this clear?
It's
Yes.
okay.
Okay, then let's continue with the last part, which is important. So if you read the historical part of this chapter, you have the point that, okay, in ancient Greece, they believed that how you see is your eyes really emanate the light, and that's how you see. Well, we can do the same in mathematically, I mean. We can do the same in ray tracing and say, okay, rather than the light sources emitting light, we can assume that our sensors emit something, like which we'll call importance. And then you actually get the exact same rendering equation. Here, the WE is really your sensors, what your sensors emit. So it's basically saying, okay, you have a point on your sensor X, and you have some direction that you assume you can see from your sensor, and you get the exact same equation. So you can, it's a dual formulation. And you can see this in the ray tracing algorithm. If you've done a ray tracer, it's a lot more efficient for unidirectional path tracing to start from the camera, start your rays from the camera and not from the lights. Because imagine that your film or your sensors are very small. If you just randomly start rays from the lights, well, the probability of hitting your film is very low. Now, if you start in reverse, which is what this equation actually does, then the probability of your rays hitting the film is 1 because you start there. Now, the probability of hitting the lights may be smaller, but you really care about measuring what's on your film. So that's the typical way to, I guess, do a basic ray tracer. And it actually uses the dual formulation. Questions on that? No? Okay, then the measurement equation, it really tells you if you multiply the light by your importance, what's the final value? So at the end of the day, you want to measure the flux for each pixel of your scene. You do not want to measure radiance. So what you show on the screen is for each pix, you want to measure the flux. If you've forgotten what the flux is, well, it's this thing, and we know how to compute this from radiance. It's like this. So what you really care about is this thing, but also multiplied by some weighting function of your sensor. It can be 1, but it can also be some specific function that, okay, you say at the, let's say, at some angles, your sensor is less sensitive, etc. So this is really it. The only mistake here in the book is that this arrow should be flipped or this arrow should be flipped. You cannot have both arrows pointing in the same way. At least it won't be consistent with their later notation. So this is just a taste of what you see in chapter 4, like this part. It's not that important currently, but yeah, they're just providing something earlier. Okay, and I think this concludes the chapter. Questions? Or if you want, we can also do a 10-minute break right now. I think that would be, okay, we can do 2 or 3 questions and then do a 10-minute break. Let's do that.
So, first of all, this measurement function, it does not depend on J. So,
No, it actually depends. So it depends on J. They just didn't write it. So this W
yeah.
here depends on J. So
yeah.
to be correct, they would have to write WJ, but they omitted the J. Yes.
Okay.
So obviously, how do you get your image in general when you do let's say when you have to program it? Well, for each pixel you have to measure the flux. So you create as many sensors as you have pixels, and then you compute the flux for each pixel. Yeah, and a pixel in your scene would be, let's say, a small rectangle on your sensor on your camera film or whatever.
Mhm.
Okay. Other questions?
Uh, I have one more question. And
Mhm.
then in rendering equation, uh, that term left from the equation L and the term L under the integral, are they really the same? Because
So these are not the same functions, but you
yeah,
can rewrite them as the same functions using this thing here.
aha, right,
So
okay,
technically you can write here, if you drop the arrow, you can write LO, and this is LI.
aha,
So you can rewrite, you can you can convert between one and the other just by flipping the arguments and doing some. So here you would need to ray trace and find the point. Where is that? You would have to find the point y, and then you would say, okay, y emits light in direction minus omega I, and then that would be the same as the light arriving at x, and then you would have the same function here and here, and
aha,
then
okay,
you can think of it as a recursive integral. The
yeah,
mathematically concrete term is a Fredholm integral of the second kind, but yeah, we will avoid that for now.
okay,
Uh,
thank you.
Other questions?
Yeah, I was just wondering if there was a bit more resource regarding the measure equation and the importance. It's kind of the part I understand a bit less.
Yeah, so that's chapter 4. In
But it's
chapter 4,
okay.
let's go. Let's just give you a feeling of where that shows up. Yeah, it's here. Yeah, here.
Okay, okay, I'll take a look then. Thank you.
And you have you get in chapter 4 you get 4 variants of it, and you can show that they compute exactly the same thing, just written in a different way. And that would, so these 4 variants can actually make more variants of those. Where is that? Let me find it. I think they introduce it here, but yeah. Based on that, you can write different. You can write your solution in different ways, and that's how you get bidirectional path tracing by considering these different ways to write it, and by solving the different ways and combining them at the end. Okay.
Okay,
More questions?
thank you.
Just one more. Is the measurement equation from 0 to 1?
No, not necessarily.
Okay,
It
because
can
you
be
said
whatever. So it doesn't need to be from 0 to 1, but after you have your estimates for each pixel, now you can apply some kind of tone mapping to get it to be nicely to have a nice representation for your screen.
okay.
So mapping this to 0, 1 would be the job of a tone mapping operator. Other questions?
I have a question. So when we in the very first part, so when we pick points from the scene surfaces, does this always work, or do you have to introduce some more elaborate way of doing this? Because I saw it's slightly different in Vich's thesis.
What are we talking about currently? What's the very first part?
This subset of points from the scene surfaces. So
You can take
I saw,
any measurable subset of points from the scene
yeah,
surface.
exactly. So is this a problem when you cannot take such? So is this a problem with like microsurface or?
No, your microsurface will be this. It will be something like that, a differential area, some neighborhood, some very small thing.
Yes, but does this always exist?
Okay. You mean, well, in the case we're interested in, so what you have in practice, everything's fine. You're working with a discrete representation. You can create pathological scenes where things are very funny and you cannot measure some sets or whatever, but in practice that doesn't really arise. So
I mean, I guess
yes,
like a fractal or something.
yeah, exactly. So if you take a fractal surface, you may have some problems, like in that case. But again, then again, it's not as terrible. Just over the fact that discretizing things regularizes them. So it may be terrible in the continuous setting, but just of the fact that you're that you're sampling it, so making it discrete, that already regularizes that problem. So in mathematics, many continuous problems may not have any solution, or the solution may not, so it may not exist, it may not be unique, or it may not be a stable solution, or so changing it a little bit, you get something terrible. So that's a new post problem. And often, if you take such a new post problem and you make it discrete, then it may even not be U post. Everything may be nice in the discrete setting. So often in practice, you usually won't have that problem. The problem with fractals in practice is really intersecting those things, because then you need numerical solvers to so numerical intersection methods, just to find the roots where you intersect them, because you can easily find the intersection of a ray and triangle, or of a ray and a sphere analytically. So just write the analytical expression, then you have everything that you need. For other things, well, you need to walk along the ray and find, okay, where's the intersection, etc. So using numerical methods. Does that answer your question?
Yes, thanks.
Other questions? No questions? Then I think we can actually end it here then.
I have a question about what is written in the book.
Okay.
Yeah, the book states that the
Which
most
page?
which page it is about different BRDF models.
Yeah, but what's the page?
I think I have to find it. It's something like 40 or 39.
39?
Yeah, right. Yeah. And it states that model called He is by 2006. Yeah, was the most advanced model. What's the most advanced model today?
Oh, I have no idea. I'm not following the BRDF literature, but I can send you a review, but it's also it's an old review.
Mm-hmm.
So I know that they have currently what they do for BRDFs. They don't even, so this he model, it's an analytic model. But what people do currently is they just take the data directly and they tabulate it. So I think the most complex model that I saw was it was I don't remember the name, but it was some data sets that they used at Max Planck for neural networks, and there it's not an analytical model. It's just they took a bunch of measurements from many different angles, and you just have like a lookup table. So I talked about this being a 6-dimensional function. So just imagine like a 6D hyper image where you can pick 2 directions. You can pick, well, probably you won't care much about the position here. So maybe you can drop it to 4-dimensional. So you can pick 2 directions and then you get exactly the what you want. Yeah, let me share the review. Yeah.
Yeah, thank you.
But I don't think in this review that this model that I saw what Max Planck was included. You can look at page 6 in what I linked to just see a tree of BRDFs. But
I see,
again,
there's a lot of them.
This is good.
Other questions?
Can you link the mathematical proof that you said about that relates the differential solid angle to differential area?
Sure, I'll find it after the meeting and I'll put it here in theory, in the channel theory. It's a I think it's from Lessig, Christian Lessig. Where and there was also a kind of dubious proof of that. Like I'm not sure it's correct in a calculus book.
Oh, okay. Thanks anyway. Yeah.
Other questions? Oh, yeah, I actually think it uses the same proof as in the, yeah, okay. I'll link you this. Where is the other? Okay, I'll link you the calculus book exercise and also this. Yeah, so the first one is other questions. If there are no other questions, feel free to go, I guess. Thanks for listening. I hope it wasn't too confusing.
No, thanks for hosting. Thanks.
Yeah, thank you for your time.
Thank you. Thank you.
Thank you very much.
Yeah, thanks for your time and for the references you're putting in right now. See you, everyone.
See you.
See ya.
See ya.